All right, in this lesson, we're going to look at parallel circuits. So what is a parallel circuit? And again, we're going to figure out how do we relate current, voltage, and resistance everywhere in a parallel circuit. So resistance is going to be a little bit trickier, but the other pieces should be quite straightforward. So parallel circuits are identified by having multiple paths for electrical current to flow. So you see current can flow out of the battery, and from there, it splits and it can go any number. There's three different paths. It doesn't have to just go through one light bulb, it can go through all three. Now, one thing I didn't mention, if you have a series circuit and one light bulb burns out, the circuit's done. It's broken and no electricity can flow. But in a parallel circuit, if one of the light bulbs burn out, electricity can still flow through the other two. So if we think of this in a car context, how would you want your headlights wired? Would you prefer to have your headlights wired in series with one path? Or would you rather have them wired in parallel with two paths, one path for each side? Well, what's the advantages for each? Well, if it's wired in series, if one, let's say your left headlight goes out, that means your right headlight goes out as well. Because they're a series circuit, the circuit would be broken. That's going to be quite detrimental should an incident happen on the road. It'd be nice to have at least one headlight still functioning. So the ideal scenario would be to have it in a parallel circuit so that if one item goes, the other item can still keep working. In general, electrical components in your vehicle are best wired in parallel simply because then if one function fails, you don't lose all functions. So imagine if a blinker light went, and because your blinker light's gone, your horn doesn't work anymore. That could be an issue. Or a fuse blows in your horn and your headlights don't work anymore. There's all kinds of things. So it's great that we can split circuits up so that one battery can feed multiple components. So parallel circuits are extremely important, even if they are slightly more complicated. In your house, you will find you use parallel circuits. Over the Christmas holidays, I spent some time doing some wiring in the basement. And what we had before was all a single circuit. So everything was wired together and we had to split them up and make multiple parallel circuits from a single source so that we could put switches. For example, like here, so we could have, say, a switch here, a switch here, a switch here, so we could switch the power for several different zones. So one of those little tricky things to figure out, but I like that kind of problem solving. I actually really like working with the electrical unit. So if I get a little geeky on you now and then, you'll have to bear with me, especially when we get to combination circuits. I love the problem solving that happens there. So Kirchhoff's laws for parallel circuits are a little bit different. You'll notice that current is not the same everywhere in this case, and that's because the current can flow through multiple paths. If there's more resistance we'll call this one R1, R2, and R3. So if R1 has a higher resistance, it's going to slow flow more, but that doesn't change the path going to R2 because they're independent. So you will find that current leaving the battery is equal to the sum of the currents going through each branch. So electricity comes through here and it splits. The three currents, the current on this branch, on this branch, on this branch, if we add them together, has to be equal to the current leaving the battery. Now, one of the disadvantages of this particular system is because it's all wired in parallel, if you're running all three bulbs, all three of them can draw more. There's less resistance because there's three separate paths, which means we're going to drain our battery faster. It's going to drain much faster than if it was in series. There's some great advantages to that parallel circuit. Now, what is the same in a parallel circuit? Well, in a parallel circuit, voltage is the same. So the voltage across each of these bulbs is identical. Well, why? Well, it's because the push from the battery comes from both sides. The push across the battery is the same push going to R1, it's the same push going to R2, and it's the same push going to R3. So the push remains constant. So that's why our voltage happens to be the same in a parallel circuit. Resistance, on the other hand, is a weird one, and it's a little tricky to explain. The equation looks strange. I'm going to give you another version of the equation in a little bit, but you'll see this is why we needed to know our fraction math. But 1 over the total resistance, or the equivalent resistance, is equal to 1 over the resistance 1, 1 over resistance 2, 1 over resistance 3. So the total resistance is inversely proportional to the sum of the inverses of the other resistances. So this is an equation that's, I find, a little difficult to explain, but it's quite easy to work with. We're going to start with working with it with fractions, and I'm going to give you a calculator shortcut for it. So in a parallel circuit, let's say R1 is 100 ohms. Let's say R2 is 50 ohms. And let's say R3 is 25 ohms. Where is most of the current going to be? Well, resistance stops flow. So the more resistant, the less current. So this first resistor, this resistor 1 has a high resistance, so it's going to have the least current. Okay, resistor 2 has half the resistance, so it's going to have double the current of R1, and R3 has the least resistance of them all, so it will have the most current. Right, so that's kind of, you can use some logic in there. That logic will help you with checking your answers. And overall, there's going to be less resistance because the flow coming out of the battery can flow through 3 separate paths, meaning it can flow that much faster than just flowing through one path. All right, calculation time. And I only have a few calculations for you, so it won't take us long to calculate. I promise I won't keep you too long. Given the circuit below, calculate the current through each branch, the current drawn by the battery, and the equivalent resistance. Why do you think I haven't asked for voltage? If you said because the voltage is the same, I agree. The voltage is the same. So let's plug that in first. Actually, we'll do our chart again. So for each branch, when we deal with each branch, we're dealing with each resistor, so we'll call them up and label them. And then we have our total, or our source. I always think of it as total, because it is a version of summing. So we know the voltage is the same. The voltage of the source is 9 volts. So the voltage across this battery, across this resistor, and this resistor has to be 9 volts. Okay, so now that we have that, we can fill in our resistances. So R1 is 90. We have 45 and 180. Now, if you'll notice, there's only one piece missing in each row. We can use Ohm's law going across each row. So I is equal to E over R. So 9 over 90 leaves me with 0.1 amps. 9 over 45 gives me 0.2 amps. And then 9 over 180 leaves me with 0.05. Okay, so they were just calculating down. Now, Kirchhoff's law says the current leaving the battery is equal to the sum of the currents traveling through each branch. So we add these three together, 0.35 amps is the current. So this is just a straight sum. This one is the same, and this one is weird. Now, we can do it without doing anything weird. We could say, well, we know the voltage and we know the current, we can calculate it. You sure can. That's definitely allowed. So let's do that. I have a computer issue. I've got a keyboard propped up on my laptop and it's hitting all kinds of buttons. All right. So let's calculate the resistance. This is going to be our Req. So Req could be, well, we know resistance is equal to voltage divided by I. So we could say Req is equal to 9 volts divided by 0.35. So I'm just taking these two pieces of information, and 9 divided by 0.35 leaves us with 25.7 ohms. Or we can use Kirchhoff's laws. Well, Kirchhoff's laws for resistance is 1 over R, I'm going to call EQ equals 1 over R1 plus 1 over R2 plus 1 over R3. I wish I had more space. So 1 over Req is going to leave us with 1 over 90 plus 1 over 45 plus 1 over 180. All right. And I'm going to send you on a wild goose chase because we need to finish the question off, and I'm running out of space. We'll finish it off up here. So we need to make a common denominator to do this question. So 180 is our common denominator, which means we need to multiply this by 2. 45 gets multiplied by 4. And we end up with 1 over Req is equal to 2 over 180 plus 4 over 180 plus 1 over 180, which is equal to 7 over 180. Our equivalent resistance. What we need to do is we need equivalent resistance on the top. So we're going to take this and flip it, and we're going to take this and flip it. Is equal to 180 over 7. We do a flip. Okay, we take the inverse of them. And this gives us 180 divided by 7 gives us an Req of 25.7 again. If I totally lost you, don't panic, don't worry. I've got another example. I'm going to give you a calculator shortcut. I'm going to try to leave a little more space on the next example. Hopefully that will help us out a little bit. Okay. All right. Next question. Calculate the missing values in the circuit. In this case, I can't use Ohm's law anywhere right now. That's the first thing I look for because Ohm's law is easy. And then I look and say, well, can I add it? Is there anything that's the same? Well, we know voltage is the same, but I don't know voltage anywhere. Current adds up, but I have too many missing pieces. I have 3 resistances and I want to know the total resistance. I can add that up. So that's allowable. So let's use Kirchhoff's law. So Kirchhoff's law says 1 over Req, or R total, same thing, is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Maybe I should have put this one first. So 1 over the total resistance is going to be equal to 1 over 30 plus 1 over 30 plus 1 over 30. So 1 over Req is equal to 3 over 30. We want to get this R by itself, so we have to flip. Whatever we do to one, we do to the other. So we get Req is equal to 30 over 3, which is equal to 10 ohms. So the resistance here is going to be 10 ohms. 10 ohms because basically electricity can flow through here, it can flow through here, and it can flow through here. It sees 1/10 of the it sees 1/3 of the resistance because it has 3 paths to flow, and they're all the same value. A little tricky to think of, but resistance is always less when you have a parallel circuit. Now we can use Ohm's law here. Voltage, so E equals IR, so voltage equals 10 times 10, which is 100 volts. Now that we know 100 volts there, voltage is the same everywhere. So we have 100, 100, 100. All right, now we can use Ohm's law here. So voltage over resistance, or E over R, is equal to I. So we can plug that in. 100 over 30 is equal to 3.3. And because of rounding, we get 9.9, but that's perfectly acceptable. 3.3 amps. All right. So not overly hard. Pretty easy calculations. This bit here with the fractions is the equivalent resistance is the most complicated piece to figure out. All right, one more question. We want to calculate the missing values in the circuit shown. So again, it's the same as before, but in this case, we happen to know the total voltage. So if you know the voltage there, we can figure out the voltage everywhere else. We've got the voltage all the way across. If we know the voltage here, we can calculate the current. So I is equal to E over R, which is equal to 12 over 4 equals 3 amps. So over here, same thing. I is going to be equal to 12 over 3, which is equal to 4 amps. Kirchhoff's laws say that we add current in order to get the total current. So that must mean there's 7 amps here. And then resistance is equal to voltage divided by current, which is 12 over 7, which gives us a resistance of 1.7 ohms. Okay, and we have all the pieces filled in. We didn't even use the horrible resistance formula, but let's double check our answer with the horrible resistance formula to make sure we know how to use it. So 1 over REQ, or R total, is equal to 1 over R1 plus 1 over R2. Now, I know Jack gives you some shortcuts for this, and that's perfectly fine, but I'm going to give you the math class version. All right? So 1 over REQ is equal to 1 over 3 plus, whoops, not 1 over 3, just a second here. Yes, 1 over 3 plus 1 over 4. I just have them flipped around, but one's a 3 and one's a 4. So we need a common denominator, times 4 times 4 times 3 times 3, and we get 1 over REQ is equal to 4 over 12 plus 3 over 12, which is equal to 7 over 12. And this is where you do your flip. So our equivalent resistance is going to be equal to 12 over 7, which gives us, again, 1.7 ohms. So both versions give us the same value, so that means we do know what we're doing calculating. We're good. Now, the last piece I'm going to do with you is I'm going to tell you how I can do this in my calculator a little bit easier. Now, if you have the calculator that we recommended, you will find it has a button. I'm going to give you this one. I'll also tell you what the button looks like, and I can tell other calculators. Right here, if you look just above this button, it has 1 over X. That's the button we're going to be looking for. Some calculators have a button that says X minus 1. Those two are equivalent to each other. Now, in this case, because it's yellow, we have to use Shift first, and then we're going to press that button. Okay, so it's going to be Shift, and then that button. You have to do both of them. So Kirchhoff's law, Kirchhoff's law uses all these 1 over R's. We can rewrite 1 over R as R minus 1. Or you'll see here 1 over X is the same as X minus 1. So we could rewrite this equation. We could say, well, REQ minus 1, so inverse, is equal to R1 to the minus 1, R2 to the minus 1, R3 to the minus 1. And we could modify that a little bit further, and we could say, well, equivalent resistance, just the final answer, is going to be equal to all these ones added together, and then the inverse button. So what we're going to do in our calculator is every time we see this button, we are going to press that 1 over X or X minus 1 button. Okay, each time we calculate. And then after we We'll do that for each of these, adding them up. Once we get to the end of our bracket, we're going to press equals, and then we're going to press that x minus 1 or 1 over x button again. So that's our inverse button. What that does is that flips the numbers around. So we'll give you an example, calculating it just on the next one. So I want you to use the equation REQ equals R1 to the power of minus 1 plus R2 to the power of minus 1 plus R3 to the power of minus 1, all to the power of minus 1. So let's plug it into our formula. So REQ is going to be equal to 15 minus 1 plus 30 minus 1 plus 50 minus 1. I never do equivalent fractions with resistances. I use this method every single time because it's so easy and quick. So equivalent resistance, 15 to the power of minus 1. You put that in your calculator. I'll give you what the decimals are, but I usually just don't write out each individual decimal. So 15, 0.066 plus 0.333, should keep a 7 on the end of this. Oops, I need another 0 in the front, plus 50. Now, one of the reasons for using this method is because with these particular numbers, yes, you could get to a common denominator of 150, but it's going to make bigger numbers. So the harder it gets to be to get, the harder it is to get a common denominator, this method happens to work better. So all of that to the power of minus 1. So what I've done at each point is I'm pushing that button in my calculator. If you're using the calculator we recommended, that 1 over x button, you do shift 15 and then shift 1 over x. Okay? Now you, instead of writing these down, you could do 15 shift 1 over x plus 30 shift 1 over x, and your calculator will keep track of all of those steps. Now adding all of those together, we get our REQ equals 0.12 to the power of minus 1. And what we're going to do is we're going to put 0.12 in our calculator, and we're going to press the button that does this minus 1 function. So shift 1 over x, or look in your calculator and see if it has that minus 1 button. And then what you're going to do is you're going to hit equals, and you will find you get 8.33 ohms. And it's actually a much faster way to calculate it. If you're not sure how to calculate any of those, please shoot me an email and let me know. I'm not in the computer lab anymore. I'm usually in my office, which is room 48. It's very close to admissions. Stick your head in admissions, she'll point you down the hallway if you get stuck. So let me know, and I don't mind at all going through this with you, or send me an email and I'll meet you in room 66, which is a larger classroom, which allows for more space and some maskless wearing, if you want to spend some time working on some calculations there. So hopefully that has given you a good introduction to the calculations needed for both series and parallel circuits, enough that you're able to work through your quiz. And next week, we will do some combination circuits and a few additional series and parallel circuits, and we'll be wrapping up our electrical unit quite shortly.